All right, then I hope that everyone who wanted to come has already joined us. Thank you everyone for coming. Thank you for joining me on this webinar titled Introduction to Emergent Design. Today I'm going to show you what are the practices of emergent design. The topic of emergent design is very large. It is, you can view it as a philosophy, as any other part of agile development. It is half a philosophy, and you can view it any way you like. So what I have chosen for you today is to show you what emergent design means in code, what it means to really design code. Before starting, let me briefly introduce myself. You may know me from my Pluralsight courses. That is where I'm exposed the most. I have about, 9 courses published there by now, 50 hours or so. These are one of the latest courses I made on object-oriented C#, on functional C#, etc. Maybe if you want to view only one course, this one, making your C# code more object-oriented, could be the best choice. It is one of the most popular courses on Pluralsight. Otherwise, you can read my articles from my website, Coding Helmet, or you can join the training on principles of emergent design, which is going to take part during the whole August this year, 15 hours, 9 sessions. You can review the content and register using this link if you like this presentation. Okay, that was the marketing part. Now let's start with the main topic of this presentation, that is the emergent design. During the next hour, you will see an example which basically goes like this. It is something like a secondary school problem. Given the numbers, find an expression which evaluates to the specified value. So we are going to write code, the program, which is going to let the user enter the numbers and the desired value, and the program is going to build an expression which evaluates to the desired value. I didn't want to bring any real business examples because that might obscure the idea. Emergent design is design of object-oriented software like any other, and you can apply it to any domain you like. For example, solving arithmetic expressions. So if you had numbers like 2, 3, 5, 7 and you wanted number 19, the program should produce something like this. Or if you wanted to use all the input numbers, then this would be the alternate solution. So the tasks to implement this will be twofold. One is to apply iterative development. You cannot imagine emergent design without iterative development. It is always going step by step. And then, while developing iteratively, you have another idea on your mind, how to produce good design. So, in light of these two tasks, I'm going to show you the development process which solves this example, where in the first half of the presentation, I will only write iteratively the program, and the result will be the design which I will be ashamed of. It's really going to be a poor design. Then we will repeat the same process, only paying close attention to the design component, and that will be the entire emergent design set of practices applied. So from this point on, the rest of the presentation will be in Visual Studio. I hope you have grabbed your coffee already. You don't want to fall asleep while watching the loads of code which I have prepared for you. So, iterative development first. We want to develop a set of features, one feature at a time. We don't want to jump onto the entire problem because it is large, it is complicated. The code will quickly become a mess. We want to add features one at a time. And when I say features, I have nothing against a simple line of code if it is doing something. So I can add one single line of code and make the application do something that it didn't do before. And I have added a feature. For example, This application is supposed to let the user input the input numbers. Okay, let the user input the problem statement. I'm giving the name to every concept. So we have a problem statement which is supposed to be solved, and I have something that will read it. Now that I have a desired solution, now I'm adding the missing components. So you have the first glimpse into the iterative development process. You write what you want to have. Then you fill in the blanks. This is the problem statement class. It exposes input numbers and the desired result. All right. It sets both of them for the constructor, and that is the entire problem statement. I can move it to a separate file, get back. All right, get back to the main function, and one component is there. Now I have the second part of this solution, and that is reading the problem statement. Even better, I could read problem statements in the loop, all until the user says no more problems for you, and after that I would exit. All right, so reading the problem statement is a function which prompts the user, inputs the numbers. You don't have to read all this code. Then it says, all right, if there are no numbers, I will quit. Otherwise, I will enter the desired result, and that's fine. So I'll remove this from view. It is really not important. This is the first feature I have. And guess what? I can even run this application. And I will show you, once it compiles, that it really prompts for numbers, and it really exits after there are no more numbers. So this is the problem. Fine. It is quiet. It says nothing. When I stop entering numbers, it exits. So I have one feature. No matter how trivial this feature is, I have one feature in my code. And then we get to the next feature that we want to add. That is constructing an arithmetic expression which equals the desired results from this problem statement. So we have this desired result, all right? We want an expression. How do we do that? Well, again, wishful thinking. Let's make a wish. What kind of code, what kind of infrastructure or whatever the domain model we want to have which lets us construct an expression? Well, this looks pretty good to me. The only problem is that I have none of these two components, but from point of view of this loop, this would be the entire solution. The expression class, it's empty right now. I don't know what exactly to put into it. I'm moving it to a separate file, but I have one component defined with its name. The next thing I need is the solve function. But look here, I'm exercising iterative development again. Well, one component in iterative development is to simply add features one at a time. There are other components there that you have to keep in mind. One is that while adding more code, all existing features must keep running the same way as they already do. You are not supposed to add more code which breaks the existing code. So, what exactly did I do? I have made a method which returns null into a variable of a class which is completely empty. And guess what? I can even print the solution found. Here it is. If it is null, I will say no solution found. If it is non-null, I will write the solution, but there will never be a solution because I'm returning null. Look, if I start this application now, you will see that if I enter some numbers and ask for a result, it will simply say there's no solution found for the problem. I haven't broken the existing features. What are the existing features? Entering the numbers, repeating until empty line is entered. Those two features are still there. And that is the crucial element of iterative development. Vertical compatibility at all costs, at all times. And then, what is this solve function? It is a kind of an infrastructure, a preparatory step before really adding the new feature. So what I have done was to transform the existing code into the next stage, which works exactly the same as before, but which is ready to accept a new implementation inside of it. So the implementation. All right. Now I'm thinking 2 steps ahead. What I want to do is to implement one specific algorithm which passes all known expressions for a queue, for a first in, first out structure, and then try to combine them with each other to construct new expressions which will go to the end of the queue and be processed later. So I'm recursively going to build as large expressions as possible out of trivial expressions, numbers initially, using 4 arithmetic operations. So this is the beginning of that algorithm. It is a queue of unprocessed expressions. While there are things in the queue, I'm going to dequeue them. If I find an expression which evaluates to the desired result, then I'm done. I'm returning that single expression as the result. Otherwise, when all the expressions are exhausted, there's nothing more to do. I will simply give up and say that there's no solution to the problem. And look, again, I have been implementing one algorithm, and this algorithm has unveiled the missing property of an expression, value. Expressions must have value. So we go to the expression and we simply say, look, you will have a value. What value? I'll give you the value. You don't have to think about it. And that's all right. This will work right now. But what exactly is this solution going to do? Well, the trick is that it's not going to do anything really, because the queue of unprocessed elements is empty already. This will return false. This will jump out of the loop and return null right away. All this infrastructure for nothing. The application will work as before. Again, that is the process of iteratively developing software. You do not break any existing behavior of the application, but you add more code which is important for the next feature you are going to add. Let's add it. What could I add to this queue of unprocessed expressions? I must have some expressions to push in, or to enqueue, not really to push. This is not stack. Okay, I'm figuring out that every number in the problem statement alone is already an expression, a trivial expression. Number 5 is an expression 5. So let me enqueue all input elements. Every number from input numbers will be turned into an expression with that same value. I'm not going to combine any numbers yet. But look, if I run this application, you will suddenly realize that I have one feature completed. Look, this larger problem, like combining to number 27, is still not going to work. But if I asked for number 4, you see, the application has found solution for number 4. So we have one feature done. And it was done in the iterative way. I don't know how to emphasize this enough. When you write code, iterative development of a line by line, a feature by feature, is a very useful technique. And I think that you should always use it, no matter what kind of software you're writing. All right then, let's continue. Let's start combining expressions. How do we do that? One way that I might do that is to keep the list of known expressions, then inside the loop, when I have this current expression, I might construct a list of new expressions by walking through all existing expressions and trying to combine the current one with the existing one, the prior one, using some method which is can combine with, which tells me true or false, whether these two can combine. You know, two expressions can be combined only if they are not already using the same numbers from the input set. If they use the same numbers, they would collide. They cannot be combined. And then that tells me that the expression must have this can combine method. And look, all the time I'm only wishing if features existed, and I just write the name of the method as I would like to have it. Are unused numbers superset of used numbers of the other one? That is plain sentence in English. You will be surprised to learn that I can implement it right the way it is written here. By adding, for example, by adding used numbers to every expression, and by implementing this method, which then asks for unused numbers, I could extend the expression to the state where it has this method implemented. And then I get back. I have to increase this piece of code a bit to supply more constructor arguments. You see, when I'm building a new expression out of a single number, I must take all numbers except this one as unused numbers, and this one is the only used number, so this is fine. You can see, you can watch this icon here, which says that the source compiles fine. All right then, if I have figured that I can combine, I will combine them using some new method which is called combine with. So I'm creating a new expression, I'm adding a new expression to the list by combining current one with the existing one using the plus sign with the value which is the sum of the values of two expressions. Now, this code is already terribly designed. I don't like this at all. But at least you can see that I'm still adding one feature at a time. I'm never breaking previous features. So right now we have iterative development implemented, but the design is missing. It is chaotic. Stay with me for 5 more minutes. I will delete everything and start from scratch. It will be much easier the next time. Right now we need the combine with method, and you don't have to read all the code. You know, this code is bad. So I need another private expression which will take care of the operator sign, the left and right operand of a binary operation, stuff like that. So I'm supporting this as requested. This is still the expression. I'm improving the printout a bit and the printout here, and I think that I'm done. No, I'm not done. This was the plus sign. Let me demonstrate you how this works with the plus operation added to the solution. And forgive me for being so, I don't know, nervous right now. This design is already too complex and too awful to work with. So let me try it. Value 14. It uses the plus operation, and you can see that this solution was able to sum up the numbers and come up with a solution. If I tried that one which used to look for trivial solutions, that feature will still be working. That is very important. I will only add the remaining operators in the same way. This is almost copy-paste. I have 2 ways to subtract numbers, 1 way to multiply them, and 0 to 2 ways to divide them. While dividing, I have to check that there is no division by 0, that the 2 numbers are divisible. This is all formal. The end result is this terrible, terrible design, which works. One feature at a time. Following the principles of iterative development, I was able to produce a solution which, for example, finds an expression to yield number 27. All right, this is number 19. I'm not going to Check, it is 19. All the rest is working fine. All the features are the same. So I haven't broken anything along the route, as you can see. Only the design component is missing. This ends the first half of the presentation where I have shown you, where I have tried to show you what it means to develop software iteratively. You would develop one feature at a time in such a way that all the previous features remain the same, remain intact. The whole application must work the same way as it ever did, and then it suddenly starts doing one thing more than it used to do. And you always have this game. You start from the existing state of the application and you're adding a little bit of scaffolding, a little bit of infrastructure, which is all returning empty collections, empty strings and zeros, does nothing. It's full of empty function bodies because you don't want that infrastructure and that scaffolding to be used right now. You want to show that your application is working the same as it did before effectively adding the new feature. Then, when you know that you haven't broken anything, then you implement those empty bodies, those functions returning zeros and empty strings and stuff. And that is exactly what I'm going to do next. All right then. Expression class. I'm going to delete all that ugly code. This is the expression which only knows about value. Soon enough, we are going to delete that as well. Don't worry. Solve method. Well, look at it. Oh, this is disgusting. This entire method is going to be deleted. I have deleted the entire solve method. All right then. What can we do when we don't have the solve method? So forget about this line of code. It was the old idea. I'll remove it. How can we build the expression builder, the solver, which is taking the problem statement and constructing the expression which evaluates to the desired value? Well, wishful thinking again. I'm not going to write a function which solves the problem. I'm going to imagine there is a solver. Well, not just any solver, an exact solver. Because some problems will not have solutions. You cannot just generate any value out of any numbers. So I want the exact solver. Now, what is it going to do? Let's see. For a given set of numbers, you can imagine that there are many possible solutions, not just one. You can construct the same value in several ways given the same set of numbers. So I will imagine that this exact solver is going to give me solutions, 0, 1 or more solutions for the problem. And then, right now, right in this situation, I don't care about any other but just one solution. So I'm writing the code the way I would like it to execute on this, in this place, in this main function, inside of this while loop. I just want to pick any solution for the problem, if any. So if there is a solution, then I want to print it out in this way, like taking the expression, printing the equal sign, and then giving the value to which it evaluates. This is the report I want to see on the screen. But I'm aware that this problem might not have a solution. So beyond this point, beyond this closing parenthesis, I have either one string or no strings at all. So I have to plug this with a default which says no solution found. And then I want to write this. I want to print this report, either this one or this one, on the console. Again, this is wishful thinking. This write to doesn't exist, this doesn't exist, this doesn't exist. the rest exists. So the next thing I'm going to do is to implement the missing parts. This write_to will be an extension method on the string. Here it is, you can look at it. I'll move it to a separate file. So this is a utility function which simply writes a string to the text writer. That was infrastructure, you can ignore that. Now, the fundamental problem is this. I'm missing the exact solver class and I'm missing the solutions for function. I will define the class exact solver. Right now, everything I'm doing is just to satisfy the compiler with the minimum possible implementation which works, which compiles. Look at this. This is the solutions for method which returns an empty sequence. If you remember the first solution, the first stage which I have hit in the iterative development was a program which doesn't solve the problem. So I have it here again. If you don't trust me, I will run this program with empty solver. I will ask it for anything and it will say that it couldn't solve it. Not even trivial solutions can be found. But I'm all right with that because I'm still developing code iteratively. Only this time I have added the design component to the table. I want to stick with the design principles, with single responsibility or interface segregation and stuff like that. I want to implement all the good practices of object-oriented design in my code while developing it iteratively. What is the single responsibility here? Okay, I have about 2 responsibilities at least, but that's not too much of a problem compared to that solve function which is doing everything. I can survive choosing the solver, delegating the call to it, and preparing the printout. So this is the responsibility of this entire program class. Everything else will live somewhere else. For example, here. And then we start implementing this. Again, I will implement that same algorithm which we already had. And the first feature was, if you remember, to add trivial solutions to the output. So I can start from input numbers and say that every number here is an expression in itself, but I'm only interested in numbers which are equal to what was desired. And then I have to construct an expression. But now, listen, in the previous solution, I used to construct an expression with the value. This time, I'm paying attention to the design, and I want every concept to have its own name, to be known by the name and recognizable among all other concepts. Those are the principles of object-oriented design. So, what do I want to return? What kinds of expressions? I want to return an expression which is a number, which is also known as the literal. So I will construct a new class, call it literal. Here it is for you to see it. The literal is a number. It will fill the number into its base, but now the base class, expression, is not going to be the class which I will use. I will turn it abstract, so nobody can construct an expression. Everyone will have to construct a concrete expression. This constructor is now protected. There is no way for me to tell the expression value. The expression will have the value which comes out from its nature. You will see we will have operators, operator expressions later, and they will evaluate the value. And now, for every number which is equal to the desired number, I can return the literal. I can just wrap that number into the literal expression. And look, I have added another feature to the program. If I enter these numbers, I can solve number 5. It will construct a literal expression. It will not solve anything more complicated than this, but I'm fine. I have one feature more. So I'm walking the same path as in the first iteration. I'm adding the same set of features in the same order, one at a time. At every moment, I'm trying not to break anything that already used to work. Only I'm following the principles of good design this time. All right, next feature will be that expression combining. Combining expressions was the thing that added enormous complexity to the first solution I made. I want to avoid all that. And you will see how by applying basic principles of object-oriented design. There will be the queue of unprocessed expressions again, so I'm implementing the same algorithm as before. The queue will initially be populated with literals. Every input number will be turned into a literal. I will still dequeue items from this queue. Again, if the item equals the desired result, I will return it, only this time with yield return, because this solver is supposed to return all the solutions, all exact solutions to the problem. But now look, the next step. I used to keep the list of known expressions. I used to iterate through them and to combine the current one with them. And that was the first very complicated, too complicated part of the solution. This time I want to avoid it. Again, wishful thinking. I just say, look, you known expressions, you merge yourself with my expression, which I have in my hand. Then, now, when you introduce new components, it is a two-way communication. It is not only that I am delegating to this object, whatever it is, and I'm just going to discover with what this object is. I'm delegating this part of the duty to that object, but then I realize that merging this expression with known expressions would produce new expressions. I suppose that those new expressions would be stored inside of this object, but on the other hand, I need to know about them so that I can put them into the queue. So let's ask this object for new expressions so that I can enqueue them. And guess what? Let me just declare this variable. It will be some expression set. I have no idea what this is. I have given it universal name like set. Set is anything. But the point is that after writing things this way, this function is implementing that same algorithm as before, and it is complete. I will only declare this expression set to make it compile, so this compiles now. This is expression set. Let me put it into a separate file so that we can see it better. It must expose merge with, it must expose new expressions getter. But what is merge doing? Well, sorry, nothing. What are the new expressions? There are no new expressions ever. The point of this maneuver is that I have implemented that complete algorithm here, and I will not have to touch this function ever again. So I have the emergent design in its finest here. I have let this expression set emerge as a design element out from this attempt to implement this algorithm which passes expressions through the queue as long as there are expressions, piling them up onto some pile, combining them, and returning every expression which has the desired value. So it was a bit complicated to tell what this function is doing, but this function is complete. It's not going to change ever in the future. Suppose that you have a performance problem with expression set. Well, this function is not going to be affected. You can change the implementation of this expression set and solve the performance problem of this algorithm without changing the algorithm itself. That is the good design. And now, again, all this juggling will produce no changes in observable behavior of this application. I can find trivial solutions. I cannot find anything more complex than that. The complete observable behavior of my application is exactly the same as it ever was. And then you step into this new component and implement its own set of behaviors. Okay, so this expression set is going to keep the list of known expressions. So that list which existed in the first solution is now part of this expression set as the only state it has. Merging will be complicated. Okay, one thing will be to add the new expression to the known expressions set so that it can be part of merging in subsequent steps. But now, how do we merge anything here? Look, I came to an ingenious idea to let somebody else do that. The single responsibility principle again. This class is supposed to represent the set of expressions. Merging expressions is a very complicated operation. You remember from the first solution, those operators were the ugliest part of the solution. They added a lot of state to the expression. They added 20 lines of code in the middle of that solve function. That is where complexity hides in this problem. So I'm just going to separate this class from that problem and delegate solution to somebody else. And I know that somebody else are the arithmetic operators. So I will say there are operators which know how to combine all the known expressions with the new expression. And then I want them to communicate back what happened. The operators will give me the new expression. So my caller is asking me for the new expressions. Well, sorry, I don't know them, but I know who does know. Those are the operators. They're not storing any expressions. They are just giving me the fresh expressions by combining this list with this new expression. I will need a private setter here in the new expressions. Initially, new expressions will be empty because there were no merging yet. And that is all. Let me just declare these expressions and you will suddenly start feeling better. I will say that I want basic arithmetic operators. And I will create them using new. Now, I haven't addressed this before. You may have been asking why I'm newing everything. Shouldn't I receive operators as a constructor argument, as a dependency? Well, maybe. Here's the trick. You want to have dependencies to decouple a class from a concrete implementation which it uses. However, I don't care about that right now. I have no operators yet. I'm still not ready to generalize them. I'm still not ready to, and I don't have to support open-ended list of operators. The task I'm solving is generating expressions using 4 basic arithmetic operations, and that's all. If I had tests, then I would probably want to mock operators, and then I would add an I operators or something, either an abstract class or an interface, and inject that through the constructor of this class, and then I would be able to construct the expression set in production settings, which would receive this basic arithmetic operators, whatever it is, a concrete class, or a mock, a replacement in tests. But I don't have tests. I don't have that situation in my hand, so I'm not doing that. On the other hand, this is the typical pitfall. You may say, I don't care, I don't have tests, I will think about injection when that happens. And then construct operators right here, like, well, not this operators, but you put new basic, etc. Here. Now, this would be the design flaw. Look, now you have tied the function, the implementation with the concrete class, and that is bad. This operators is decoupling the merge with function from a concrete class, because I don't care what this is. Tomorrow I might have an interface, I operators, which also exposes combine, and this method will keep working. So the point of all this is that if you expect to have a decoupled design in the future, then you should have separate variables, separate slots. You will read in literature that this is called a seam. So there is a seam in this class which lets you inject a variable later when it becomes a reality. Before having two implementations of operators becomes a reality, you don't have to care about that. I hope you have understood what I wanted to tell. The point is, again, that you don't tie your implementation with any concrete implementation, but only with the interface, with public methods of this, so that you can later substitute that with whatever class or interface exposes the same interface, and you will be happy. So, basic arithmetic operators. I will define them, move them to a separate file. Let's return here for a moment again. Look, this is done. This is also done. This complete expression set is final. I'm not going to change it ever again, except its constructor, but constructor is not part of the public interface. So I have another small isolated component which is done for good and combined with other components to make the whole system work. What are the basic operators then? And how are they going to combine? They have to combine this. Okay, there will be a little bit of link here. I will walk through the expressions, ask each of them if it can combine. I'm not going to ask them. I'm going to implement that in this class. So can combine will say that use the numbers of the one and use numbers of the other one intersect to an empty set. So any, and this here false, will say that intersection of used numbers is an empty set. This is mathematical definition of the ability to combine two expressions. Then when I know that I can combine this expression with that one, I will really combine them, and combining will produce 0, 1 or more expressions as the result. So this is the combine, but look, oh, operators. So that is the complicated part of this solution. I have chosen to delegate this to yet another component, to some operators. And what are the operators? Oh, a binary operator. Oh, a list, a sequence of binary operators. All right. Right now, I have no binary operators. That is iterative development again. On the other hand, it turns that the expression must expose used numbers. I only have literal, which will simply say its own value as the only used number. So this is plugged. Now, binary operators. Okay, abstract class for binary operator, which only knows how to combine two expressions, no more lists of expressions. I don't know, maybe you have already lost me on all this volume of code, but you don't have to get into every detail. The only thing I want you to start feeling is that process of pushing all responsibilities except one to your dependencies. And that is all. So you choose which one responsibility you want to implement in any place you find yourself. Implement that one and delegate everything else to your dependencies. So I'm going to speed up a bit. I will introduce an add operator, which will produce, guess what? A binary expression Now, binary expression is another kind of expression which has a left child, a right child, and a symbol, and it will receive a value, evaluated value for the constructor. You don't really have to read this class. You only have to understand that I had the need for binary operations, binary expressions, and I have implemented them. And this is the addition operator. So here in the basic arithmetic operators, I will say that there is an addition operator. The solution compiles. I will show you that this program now knows how to add numbers. Here, it is adding numbers. So I have one complete feature done. And of course, I expect the existing features to keep running as before. Finally, I will only add the rest of the operations, subtraction, multiplication, division. Those will be separate classes. Why separate classes? Because they operate in different ways. This is division. Division is not always possible. It is also non-commutative, so you can have 0, 1, or 2 possible division expressions. So here it is. It will either return 0, 1, or 2. It will check whether there is possible division by 0, whether two numbers are divisible, and it will return 0, 1, or 2 expressions. Multiplication is commutative. It will always produce one result. What else do we have? We have subtraction, which is also non-commutative. It will construct two results, and that is it. So now I have 4 basic operations. I can run this application and it will solve all the problems as before. Here you have the entire solution. All right. This is the final form of this program. You may observe that number of classes is growing, but not all of these classes are the same. These operators are concrete implementations of this binary operator abstract class. What you would normally do in your practical applications, you would create a sub-namespace and put all concrete implementations one level deeper than the abstraction they implement. So suddenly you have 1/3 of the classes disappearing. When I say disappearing, they really disappear. You don't see them. You will never open these 4 classes because they work, they are doing one thing only. You will never have to change them. You will never have to look at them. In a large project with thousands of classes, you would have deeply nested structures, deeply nested namespaces. And again, you would always only look at one level and see maybe the problem is there, maybe the feature you're adding is here. If not, you would jump one level deep. But when you jump one level deep, then you don't care about anything above. By organizing classes into sub-namespaces, you're removing concrete classes from sight. At every level, you only have the basic concrete classes you are dealing with, plus a few abstractions, which these depend on, and that is all. Now, if you keep pushing this same logic, which I have tried to show you in this demonstration, you might end up with something like this. I think that there are nearly 100 classes here. Do you know what this solution is doing? It's also solving arithmetic expressions. See, these are the classes. So when I mentioned that training 15 hours long, this is the result of 15 hours of coding. That is what you would usually hear under the name deep domain model. This is really deep domain model. For example, I can transform expressions in about 15 different ways. I can add parentheses to them. You see, this is one typical transform parenthesizer, which is a minimal parenthesizer. You guess that there is also a full parenthesizer side of it. But when you yield such a deep and detailed model where everything is really decoupled and everything is connected through abstractions, then you can use that model to do tremendous things. For example, I can start from an exact solver and this problem and ask for all solutions, exact solutions where there are no unused numbers. So all 4 must be used. Take any one of them, print it out. Right. Or, that was easy. Or I could start from all solution stream, enumerate all of them and count them. And see how many distinct expressions are there. Or I could start from all numbers between 1 and 100, then accept all solutions constructed by with these numbers, where solution, this was not important, I could even delete it, and pick the value of every solution, all right, and then select this range, accept all possible solutions with these numbers, and tell you how many of the first 100 numbers cannot be constructed using these numbers. Or I have an approximate solver. So I have problems when I run this, you will see that number 79 cannot be constructed using these numbers. Okay, so I can ask for an approximate solution to this problem. And I will write that. So solution closest to 79 will be this one. Or look at this, problem generator. I will pick all the solutions, enumerate for them, which have used all 4 numbers, which yield value greater than 0, group them by the value and pick only the groups with one single solution in them. For every group I will take that one solution, and also I have one additional requirement. That solution must not end in multiplication, because I don't want problems which are solved by breaking numbers. And then I want to write all those solutions. I will generate problems with unique solutions. So I have reversed the task. This is what you can do when you have a deep model. You can do whatever you like. I will run this application, and with that we will conclude this presentation. If you enjoyed this demonstration, then I can tell you that there are another 14 hours of typing this same code. During those 15 hours, I will show you not only how to design, but you will see the problems that happen along the route. You will see that we will have to redesign things. We will hit design flaws, bad designs. Also, we will have performance issues. I will show you how you can fix performance issues and still deal in the emergent way. In the end, we will reach this deep domain model, which can be used in any way you like. Thank you all for joining me. I hope you have enjoyed this. I hope you have learned something new from this, and that you will use what I have demonstrated here in your everyday work.